Hello everyone and welcome to Chapter 0 video number 3 in the 3-phase induction motor course. In this video we are going to have a quick revision about magnetic circuits, looking for the main elements of the magnetic circuit. But if you want to have a deep analysis for magnetic circuits, you need to look for another video, not this video. Also, we are going to cover self-inductance, torque production in electrical machines, which is very important for a machine like induction motor. And also we are going to cover the concepts of power, torque and speed calculation. Once we finish this video, we'll be ready to start the 3-phase induction motor course. So what is the magnetic circuit? To answer this question, let's look for the electrical machines, either static or dynamic. Static like transformer, dynamic like any rotary machine. So the machine consists of a combination of ferromagnetic materials and air gap. So for example, rotary machines, we have stator, air gap and rotor. So either stator or rotor or both are wound by a coil, has a certain number of turns N. If we inject a current inside this coil, so we have a magnetic flux. So in most electrical machines, and we are going to exclude permanent magnet from that one, the magnetic field is generated by the current passing through these coils. And that one will form the basic magnetic circuit. Let's look for the main relations or the main elements of the magnetic circuits. What a wordy slide! I'll leave it for you here just in case if you like to stop the video and read it. But I'm going to explain that one here. So if we have a magnetic core or iron core, as we can see here, and that one has a cross-sectional area A, and there is a coil wound here with a certain number of turns N, and we succeeded to inject a current I, we have here what we call it magnetomotive force. This magnetomotive force is going to drive a flux through this core, and this flux is going to be subjected for this cross-sectional area A. And that one is the same here without air gap, so we have the same cross-sectional area A. If you notice here, we have what we call it a magnetic flux path, so that one is L. So definitely this flux is not infinite. That one is limited, and limited by a term is called the reluctance. And the reluctance is function of the physics of this core. So the magnetic length path over the core area or the perpendicular area that the flux is going to be subjected for, and we have what we call it permeability. So we have the permeability of the space mu node equal 4 pi 10 to the power minus 7, and please note that one has a unit, Henry per meter. And mu r is the permeability of iron, and that one something like 1,000, 2,000, 20,000, it depends on the iron material. And this is why I said that the reluctance is function of the material and the physics or the structure of this core. So here we have something like a balance equation that's Ni should equal this phi multiplied by the reluctance. And this reluctance is going to limit the flux. But at the same time, we have here a relation between the flux phi and this area. And that one is the field density B, flux density. So that one is flux phi over area. And B has a relation with the field intensity H. B equals mu node mu r H. And most of you knows that we have something is called BH curve. So that one is H and that one is B. So the relation between B and H is mu node mu r. So this equation, which is Ni equals phi r, can be changed to Ni equal HL. So where L is a magnetic length path and H is field intensity, and that one is ampere turn per meter. Right? But we notice here that you write in the equation sigma, but you write here in this equation Ni equal phi r. Because here we have one loop, so we can say that's Ni equal phi r. But to generalize the equation, just in case we have multi-windows, so we can say that's Ni equals sigma phi r. So please take some time to read this text, which explains what I did here. And that one is going to give you an idea about these elements. So we have here Ni is the magnetomotive force, flux phi in the units of Weber, reluctance equals L over mu node mu r area in the units of ampere turn per Weber, flux density equal phi over area, and B at the same time equal mu node mu r h. H is the field intensity in the ampere turn per meter. What is the analogy between magnetic circuit and electric circuit? If we have a magnetic circuit like this one, we have a coil with number of turns N, and we have iron core with cross-sectional area A, and we have a current injected to this coil, so we have here magnetomotive force equals Ni. So we can represent that one something like a battery here, because that one is going to drive a flux phi inside this iron core, as we can see here. So this one will be the flux phi. So this flux has a magnetic length path L, and we have here a cross-sectional area A. So definitely we have a reluctance for the iron material and the reluctance for the air gap. So we can calculate the reluctance of the iron as L over mu node mu r area. L is the magnetic length path, and area is the cross-sectional area that where the flux is projected to. And we have here mu node, the permeability of the free space, 4 pi 10 to the power minus 7 Henry per meter. And mu r is the permeability of the iron, could be 1,000, 2,000, 20,000, it depends on the iron material as we mentioned before. So for the air, we have mu node, but mu r equals 1. So mu r for the free space equal 1. And the length here for the air gap is G or LG. So we can write that one G or LG, it depends. So the circuit now will be Ni should equal phi multiplied by Ri plus Rg. Also, we can write that one something like H multiplied by Li plus Lg. We know the relation between B and H, so B equals mu node mu r H. B is the field density, so that one is Tesla or Weber per meter square. H is the ampere turn per meter field intensity, right? So now we can make the analogy with the electric circuit. The Ni, which is MMF, can be represented by a battery or voltage V. So the flux phi can be represented by the current I, and the reluctances can be represented by resistance. So Ni equals phi multiplied by sigma resistances. So something like V equals I multiplied by sigma resistances, Ohm's law. So from now and then we can analyze the magnetic circuit similar to the electric circuit using Ohm's law, Kirchhoff voltage law, Kirchhoff current law, using the symbols or the elements of the magnetic circuit. And that one is going to simplify the analysis of the electrical machines later. In the previous slide, you explained to us the analogy between the magnetic circuit and the electric circuit, but you didn't explain why we have the flux in this direction. So we have what we call it right hand rule or right hand screw rule. So you are going to have the direction of the current will be in the direction of your thumb, and the direction of all of your fingers will be the direction of the field. So let's look here. If the current is into the paper or into the screen, so the flux will be in this direction, right? But if the current is out of the paper or out of the screen, the flux will be in this direction. And if you are going to apply this rule, you are going to identify the direction of the flux in your magnetic circuit or in your electrical machines. Also, we like to calculate the self-inductance and what we call it leakage inductance. If we have a magnetic circuit like this one and we have a coil with number of turns N, and there is a current I injected to this coil, now we know the direction of the flux phi. So if we multiply N by phi, we have what we call lambda flux linkage in Weber. And we can express lambda as Li. L is a term called self-inductance, and I is the current injected to this coil. So L can be expressed as N phi over I. Phi equals BA. A is the cross-section area of this core, right? So that one is area A. So B is the flux density in Weber per meter square or Tesla, but B can be expressed as mu H. So H is the field intensity in ampere turn per meter, and mu is the permeability, mu node mu R. We know the equation that's Ni equal HL, so we can write that I equals HL over N. So substitute that 1 here. So in this case, L equals N square mu H area over HL. So we are going to cancel H with H. We know that the reluctance equal L over mu area. So that one will be N square over reluctance. So this equation tells us that the inductance or self-inductance of the coil depends on the squared of number of turns and the physical dimension of the core, area or cross-section area, the length of the flux path, right? And the permeability of the iron, how the iron is good, right? When we are going to inject the current, not all the flux is going to link here. We have flux, some flux lines are going to escape here. We call it leakage flux, phi leakage. So we have another inductance is called L leakage, right? And that one equals N phi leakage over I. So that one will be the leakage flux. When we are going to analyze the induction machine later on, we're going to find leakage inductance and linkage inductance, or what we call it self-inductance or magnetizing inductance later on. So inductance or the flux is going to link between the stator and rotor and some leakage flux. So we are going to express that one by inductance, magnetizing inductance and leakage inductance. We are still with this magnetic circuit. If we have the coil with number of turns N and the current I, so we have a flux phi. But if we apply a sinusoidal excitation here, we have a sine function or cosine function. So this flux could be sine or cosine. So let's assume that our flux is phi maximum sine omega t. We're going to apply Faraday's law, where Faraday's law E of t, induced voltage across this coil will be d lambda by dt. And you know that's lambda equals n phi, so that one equals minus n d phi by dt. So in this case, E of t equals E maximum cosine omega t. Please note that the voltage is cosine, the flux is sine. There will be a 90-degree phase shift between the voltage and the flux. So we are going to look for E maximum, how to calculate RMS value. So E maximum over root 2, 1 over root 2, N phi maximum, omega equals 2 by F. And we are going to rearrange this equation, and that equation will be applied to all AC machines, transformer, synchronous machine, induction machine. So we have ERMS equal 4.44, a constant, phi maximum, maximum flux in this core, supply frequency, and the number of turns N. So definitely that one will be modified for three-phase machines, something like synchronous or induction. So this N will be number of turns per phase and the other factors according to the winding rearrangement. But this equation applied to all AC machines. What we need from this equation that the voltage here depends on the frequency and the flux and number of turns. So what about torque production in electrical machines? I consider this slide as one of the most important slides in this video. So torque production in electrical machines, either we have what we call it saliency torque. So the machine structure depends on the reluctance. So the torque is proportional to the rate of change of the reluctance with respect to the position. And that one, it depends on the inductance and the reluctance relationship. Remember that inductance equals N square over reluctance. So if you have a variation of the reluctance, you can have a saliency torque. Another type is called induction torque, where the torque is proportional to two fluxes, phi 1, phi 2, and sine an angle between them. So that one's similar to a flux in the stator and flux in the rotor and sine the angle between them. If you achieve angle between the two fluxes 90 degrees, you can maximize the torque, where torque is proportional to phi 1, phi 2. So can you give us examples? Saliency torque, something like stepper motors, but induction torque, something like induction motor. Let us wrap up this video by some well-known concepts. The torque T in Newton meter equal J alpha. J is the moment of inertia multiplied by the angular acceleration in meter per second square. And the angular speed omega in radian per second. So the relation between the angular acceleration and the angular speed in radian per second, alpha equal d omega by dt, where omega equal d theta by dt, and theta is the angular displacement or the angular position. And from this one, alpha equal d2 theta by dt square. The work equals torque multiplied by the angular displacement, so the work equals integral torque d theta, and the power equals the rate of change of energy, where P equals dW by dt. So the instantaneous power due to the torque and angular velocity, very important equation in electrical machine, power equals torque omega. Power in watt, torque in Newton meter, and omega in radian per second. So usually we express the speed in RPM, even that one is not SI units, but we need it in RPM. So in industrial commercial products, we use the speed in RPM. So 1 radian per second equal 2 pi over 61 RPM revolution per minute. But very, very important equation we use in electrical machine analysis, omega equals 2 pi n over 60, and n is the speed in RPM. So two equations from this slide are very important to me, that power equals torque omega and omega equals 2 pi n over 60, where n is the speed in RPM and omega is the speed in radian per second. As a summary for this video, we covered magnetic circuits, what is the analogy between magnetic circuit and the electric circuit, and how we're going to analyze the magnetic circuit, where we have main elements for the magnetic circuit, something like the flux phi in Weber, the field density or the flux density in Weber per meter square, or Tesla field intensity, ampere turn per meter, and we can solve the magnetic circuit similar to the electric circuits using Ohm's law, Kirchhoff voltage law, and Kirchhoff current law. Also, in the magnetic circuit, we noted that we have something similar to the resistance, which is the reluctance, and the reluctance function of the physical dimension of the magnetic core. So reluctance equals L, the length of the magnetic path, over mu naught mu r, the permeability, which it depends on the iron material and the air, multiplied by the cross-sectional area A. From this one, we can calculate what is called self or leakage inductance, where L equals n square over reluctance. If we have a sinusoidal excitation applied to this magnetic circuit, the induced voltage E equals 4.44 phi Fn. So the induced voltage depends on the frequency, the magnitude of the flux, and the number of turns. How the torque is produced in electrical machines, we can have what we call it saliency torque or induction torque. For a machine, something like switch reluctance motor or stepper motor, we can have what is called saliency torque, where torque is proportional to dr by d theta. But for a machine like induction machine, we have what we call it induction torque, where torque is proportional to flux in the state or flux in the rotor and sine an angle between them. And we finished this video by the relation between the torque and power, where power equals torque omega, power in watt equals torque in Newton meter multiplied by omega in radian per second. Also, we can calculate omega in terms of the speed in RPM, where omega equals 2 pi n over 60. What will I watch next? So in the next chapter now, that's we're going to have a chapter number 1, we're going to start the rotating field. And this is the first step for induction machine. See you in the next video.